In this video, we will be covering how to calculate the change in velocity and pressure of a fluid flowing through a pipe when it experiences a change in area. By the end of this video, you'll be able to calculate the change in pressure between 2 points in the pipe and use this knowledge to solve similar problems. Let's begin by looking at the given problem. The problem states water flows through a horizontal pipe with a radius of 0.1 meters. At point A, the velocity of the fluid is 5 meters per second and the pressure of the fluid is 650 kilopascals. The radius of the pipe then decreases to 0.05 meters at point B. The height of the pipe remains constant. The question requires us to calculate the following. A. What is the velocity of the fluid at point B? And B. What is the pressure of the fluid at point B? We will begin by writing down the information given to us in the problem to help us solve it. It tells us the density of water ρ equals 1000 kilograms per meters cubed. The acceleration due to gravity g equals 9.8 meters per second squared. R1, the radius of the pipe at point A, equals 0.1 meters. H1, the height at point A, equals 0. P1, the pressure at point A, equals 650,000 pascals. V1, the velocity at point A, equals 5 meters per second. R2, the radius of the pipe at point B, equals 0.05 meters. H2, the height at point B, equals 0. And we are going to find V2 and P2, the velocity and pressure of the fluid at point B. Sub-question A requires us to calculate the velocity of the fluid at point B. We can do this by using the continuity equation. A1V1 equals A2V2. The continuity equation tells us that the area and the velocity are proportional to each other. This means that one cannot increase without the other decreasing and vice versa. So, to use our equation, we already know V1 is 5 meters per second as it's given to us in the question. We can calculate A1 and A2 by using the radii for the pipe at both points. As the area equals pi r squared, the cross-sectional area of the pipe at point A is pi times 0.1 squared, which equals 0.031 meters squared to 3 decimal place. The cross-sectional area of the pipe at point B is pi times 0.05 squared, which equals 0.008 meters squared, again to 3 decimal place. We can now add these values into our equation. The only thing left for us to do is to find V2. We can transpose our equation to find V2, giving us 0.031 times 5 divided by 0.008, which equals 19.375 meters per second. We can check that this is consistent with our expected answer, as the cross-sectional area of the pipe decreases by a factor of 3.875. The velocity of the fluid increases by a factor of 3.875 also. Sub-question B requires us to calculate the pressure of the fluid at point B. This can be done using Bernoulli's equation, shown on screen as P1 plus ρgh1 plus half ρv1 squared equals P2 plus ρgh2 plus half ρv2 squared. We must note that, as the velocity of the fluid is increasing and an increase in velocity causes a drop in pressure, we must expect a lower pressure for P2 than we have for P1. As the height is constant, this term in the equation does not change and can be cancelled out. The equation then becomes P1 plus half ρv1 squared equals P2 plus half ρv2 squared. Rearranging this equation for P2 gives us P2 equals P1 plus half ρv1 squared minus half ρv2 squared. Or we can simplify this by factoring out the half and the rho to give us P2 equals P1 plus half rho v1 squared minus v2 squared. Once this is done, we can go ahead and plug our numbers in to find P2. So we know that P1 is 650,000, rho is 1000, V1 is 5 and V2 is 19.375. Multiplying out our brackets gives us 650,000 plus half times 1000 times 5 squared minus half times 1000 times 19.375 squared. This equation becomes P2 equals 650,000 plus 12,500 minus 187,695, which equals 474,805 pascals. As there has been an increase in velocity of the fluid, and our value for P2 is lower than our value for P1, we know our answer is consistent with the expected answer. In conclusion, our value for velocity at point B was found to be 19.375 metres per second, and our value for pressure at point B was found to be 474,805 pascals, or 474.8 kilopascals. So there we have it. We've successfully solved the problem using continuity equation and Bernoulli's equation. Thank you for watching. Please keep checking our channel for similar engineering education content.